So this is an important capability or feature of Cimerix MP, the CFD tool, that we use a lot. Sometimes you're using it and you don't even know you're using it, and I'll show an example of that, but also it's useful explicitly when you do intend to use it. So what that's about is this is our propulsion analysis that we had done before. If you recall, I think the last thing we did is we added a section plot for a propulsion analysis. One of the neat things about the section plot that you see here is you can see this is what I've plotted on this cross section in the model is longitudinal velocity, and you can see the increased velocity patterns where the propellers are. This is a good indication that you know this is a self-propelled run, because in a resistance run, you'd see a deficit in flow because of the struts and the appendages, but you wouldn't see this acceleration of flow, which is there because of this virtual propellers, these actuator discs. But anyway, what I wanted to show here is there is in the user interface, and it shows up in a couple different places, but in the latest version, at the top of the screen, there's this little A equal question mark symbol, which when I click it, opens up something called the expression editor. And generally, this is where you can define your own information about the run for various purposes. As I show in the slide here, you can define expressions that are used in the other parts of the user input of the user interface as input to Cimerix. You can create lookup tables. You can create custom plot and display variables. So sometimes you'll say, how would I just plot this on the surface? And it's some value that's derived from another value but doesn't exist natively. You can define your own custom variables to plot. So that's mainly what that's about, but let me show you a couple of examples to give you a better feel. First of all, you'll see there are already some information in here for a self-propelled run. Orca and Rhino, when they generated the simulation, put this information into the global expression editor. And the interesting thing to keep in mind about these variables or these definitions is that they can be used in various ways through the interface. The top pieces of information that you'll always see, even in a resistance run here that I'm highlighting, are the hydrostatics properties that were calculated for your vessel from Orca. And the reason we put these in here is one of the things I showed you in Orca is the ability to create a report in Excel, either a resistance report or a self-propelled report. And part of the ability to calculate that report is to know the hydrostatics that were used at the time the simulation was set up. And this is where we get them from in our reporting. So these are in here automatically from Orca, and they're really just there for reporting purposes. But there are other variables in there that are used for other purposes. For example, this was a self-propelled run. And if I look at the marine module here, so over here on the left of the interface, I selected the marine module in the model tab. Make this a little bit wider so you can see it. And when you look at the properties of the marine module, one of them is your propulsion option, and it says it's self-propelled. Remember, this was the case where we have a propeller pushing us along. It's not a towed resistance run, but it's a self-propelled run. And if I expand that, you can see there's a propulsion source, which is a propeller model. So that is what is the definition of this propeller that I was showing you in the section plot here that's causing this, this flow acceleration. It's defined by this propeller model. And if I expand that propeller model further to see its characteristics, you can see things like its location, which came from Orca and Rhino, and its direction. But a couple of things in here are not numbers, but variables. So for example, what RPM is the propeller turning out? It says it's turning at PRPM1. Now I could just, this happens to be the 218 RPM case. You could have just typed in 218 RPM, but instead it's using a variable. And in addition to clicking this A equals button to get to the expression editor, Whenever you have a variable that can be defined by an expression, if you select it, you get the little a equal. It's very small here, so it's very hard for you to see, but this is a little edit expressions button. So it's the same thing. It opens the expression editor. And what you see in here, if I expand this, is that PRPM1, the RPM of the propeller, is defined right here as 218. So it's defined as an expression. We defined it as an expression in Rhino and Orca when we created the simulation. So if you wanted to change the RPM, all you do is just change this number right here and then start the simulation. You'd have to stop the simulation, change a number, and start the simulation again. So there's an example of how an expression is used in here. Say you wanted the RPM not to be constant, okay, but instead you wanted the RPM to be a variable. In other words, you wanted it to change over time. You could actually put an expression in here that said PRPM1 equals time less than 5 question mark 100 colon 218. What does that mean? I'm going to put a couple spaces in here so I can call it out a little bit better. That's an expression that says, first of all, it makes use of a variable called time. Where's time defined? It's nowhere in here. Time is a special variable that is defined in the simulation. Any simulation you run in Simerix, there is an automatic variable called time, which is the time of the simulation. How far along in the simulation am I? So what this expression says that is, while my time is less than 5 seconds, because the units are seconds, use 100 RPM. But as soon as my time reaches 5 seconds and then beyond 5 seconds, go over to 218 RPM. So this would be a way of defining a propeller RPM that changed into 2 different values. That's just an example of an expression. And so it would use that in here. Now, if you want to leave an expression in there because you might want to use it in the future, but you don't want to have it be active right now, you just put a pound sign ahead of it. The pound sign or hashtag is the symbol that means these are comments. These are commented out. Don't use them. They're not live. I'm leaving them there from reference. So that means you can use that also for doing things like making comments. Like say, below is the expression for a variable RPM. When as soon as the interpreter of this expression editor sees the pound sign, it just ignores anything else on the line. So so right now everything's still the same as it was before. I just added some information. Okay, so that's an example of creating your own variable. You can define it, name it anything you want, as long as it's not an already pre-used or pre-named variable. So I called it PRPM1, and it's equal to 218. So that's one use of an expression. You can see also in this propeller model, there's a couple of other expressions. The thrust curve, or the thrust value that's generated by the propeller at that RPM, is defined by a variable called KT1. And the torque value at that given instant in time during the simulation is defined by a variable called KQ1, the torque coefficient. What's interesting about those variables are that they're not defined in a normal way, like just a value or a simple expression. They use this keyword table. That expression table means these values of KT1 are defined elsewhere in a file in the form of a table that I'm going to look up. The name of the file is called kt1.txt. It's a text file. What I'm going to look up in there to get KT1 is I'm going to look it up in a value of wake fraction 1 times marine prop J1. So if I go back over to my file system here and I go into the mega yacht propulsion example, which is what we're looking at now, and we're in the 218 RPM example, sure enough, you see a file here called KT1 and another one called KQ1. These were generated automatically by Orca, so you don't have to worry about creating them in this case. What I'm trying to show you is that you have that ability to create a text file that you use as a lookup table and interpolate values out of there. So if I were to open up this file and look at it, let me make it a little smaller because it's taking up the whole screen. If I was to look at that KT file, you would say it's a table of KT values, thrust coefficients for the propeller, as a function of what we call the speed of advance, or the advance coefficient, J. So it's got two values, two columns, a J value, 0.01, and a corresponding KT value. So what this expression here means is go into that table, kt1.text, calculate this value internally, and look up the corresponding KT value in the table based on that, and use that as the thrust coefficient for the propeller. So this is another more complex example of the expression editor, where not only can you define a variable in place, but you can actually look up a value in a table, okay? And again, so far, what we've seen here has been generated for you automatically. You didn't have to type this in. Rhino and Orca generated all these expressions for you automatically, but there are times where you want to generate your own expression. For example, let's say instead of a propeller model, or in addition to a propeller model, I wanted to have I was doing a water jet analysis. So I was running a water jet, and really in Orca, the only things you can define for self-propelled runs right now are propellers. So how do I define a water jet? Well, typically from a water jet manufacturer, they'll give you thrust information about their water jet at different speeds. So you have the thrust information at different speeds. So I can come in here and say, I want to add a force vector. So instead of a propeller, I'm going to have a force vector. And when I add a force vector, it lets me give me an ID of the force vector. So I'm just going to call it force vector 1. It gives me a position. So you would place the location, the X, Y, and Z coordinates of that thrust vector at the back end where the water jet nozzle is, right? So wherever it was in your model, you'd put the X, Y, and Z numbers of that. The direction, this is defaulting to pointing directly forward, but if the water jet nozzle was pointing slightly up or slightly down or left or right, you would adjust the components of this direction vector. But then the last piece of input is the actual force from the water jet, the actual force of the force vector. It defaults to 0. So how do you get the water jet force in there? Well, you could just type in a force. It's 1,000 newtons. Okay, that's one way to do it. Or you could, maybe a better way to do it would be to define a variable called water jet thrust. Okay, and then go into the expression editor, and at the bottom define a new variable called water jet thrust equals 1,000, and newtons is implied. That's the current unit system I'm working in. So you could do that, or you could say water jet thrust equals, if time is less than 5 seconds, you could say it's 200 newtons times time. So there, when time is 0, the thrust is 0. But as time increases, the thrust increases with time linearly up until 5 seconds, at which point 5 times 200 is 1,000, will reach your 1,000. And then after that point, it stays 1,000. So there's an example of an expression where it says the water jet thrust will sort of gradually increase linearly with time until it reaches 1,000, and then it stays 1,000. Or you could put a variable that says water jet thrust equals table, and you could create a file of a called thrust.txt, okay, where you look up the value of the water jet thrust, and the input might be the current speed of the vessel, because typically the thrust varies with speed. So how do I get the speed? Well, there are some predefined variables in a simulation. For example, time, we see that's a predefined and known variable. There's one in the marine module called forward vel. Okay, that stands for forward velocity. It's predefined, it exists, it's in the marine module, and it's the forward velocity. So what this says is, for my water jet thrust, I'm gonna look up in a table whose file name is thrust.txt, and I'm gonna go into that table with the forward velocity at this given instant in time. It's gonna change over time, obviously. You would have to create that file, thrust.txt, and populate it with the data you got from the water jet manufacturer of what the thrust looks like over time. Okay, so marine.forward.vel time are two examples of predefined variables. If you go back to the presentation slide, I show you some of the other examples of available variables in the marine module. So for example, here's marine.forward.vel is the forward velocity. There's one for the pitch, one for the heave, one for the resistance. The propeller thrust and torque values and power values are all available variables. These are defined in the help file. There's also other variables for specific to other modules, the flow module, for example. Pressure is an example of one that's available. They're documented in the help file, but these are predefined and available, and what their value is the value at that given instant in time during the simulation. So this is just what I really wanted to do here is just show you this expression editor, its importance, and how it works. There's one other example I think that I mentioned but haven't shown you is how to do custom plot variables. So say, if you remember, one of the things I could do here is I could plot the power prop 1. Right, so what I'm showing here, remember this is a self-propelled run, and I was showing you the power being absorbed by propeller number 1, which is the propeller, the port propeller that I've defined on this hull. And you can see it's varying. It's a lot of power at the beginning because we're in bollard condition, right? The boat's not moving yet, so it has to put a lot of power to get the boat started. But as the boat starts to accelerate, it goes down and eventually reaches a value that's about a little above 6,000 kilowatts. So this is a custom variable. This normally wouldn't show up in a default Simeric simulation, but Orca defines this as a custom variable, and the way it does it is, you can see right here. We were looking at power, so let's go to power as the example, the very last one. So at the bottom of the screen, what you see is plot. Whenever you see plot dot, that means I'm defining a custom plot variable for the time history plots, these 2D time history or XY plots. So plot dot means I'm doing with a custom variable. This is going to be the name of the variable, power prop 1, and sure enough, what do you see on the axis here? Power prop 1. And here you set its value, which happens to be something called marine.prop power 1, which is a predefined variable. But you could also put your own custom expressions in here, anything you want in here. So that's how you define a custom variable, is this line right here, a custom plot variable. The line below it, first of all, it looks like it's a comment line because it's got the hashtag in front of it. So in general, you would think the system would ignore anything down here. But this is the one special case for a plot variable where if you put a hashtag, you put the name of the variable, like you see here, plot.power prop 1, you can define its units. Because by default, when you're defining something in custom variable, the system really doesn't know what units it's in. It's sort of implied based on the syntax, the context at which it's being used. But since we're defining a custom variable, we need the system to tell the system what units that variable is in, and we say it's in watts. So that's why I'm able to plot kilowatts or watts over here. Otherwise, if I didn't have this line, you'd still be able to plot this curve, but it wouldn't have its units. It wouldn't know its units. It would just say this is just some value that the user has tried to plot. So that's how you define a custom plot variable. We did these custom variables for you out of Orca because we know they're of interest. We know you want to see the propeller thrust and the propeller power and the torque and so forth. So we define these automatically back in Orca and Rhino when you set up the propeller definition, but you're always free to add your own expressions in here. When you define custom plot variables, the way you see them as available things to plot is you select the common module. So this model tab, one of the modules that'll always be there is the common module. And when you select comma, any custom plot variables that you've defined will show up in the list. So here's my power prop 1. And the reason these have the 1 designation is because, of course, you could have many propellers on your model, so we need a number to identify which propeller it is. Okay, so that was something I had forgotten to discuss last time, but I think it's important and that you understand it because it's used a lot, and even when you're not aware that it's being used behind the scenes because Orca defines these variables. But if you want to define your own variables, that's how you do it. So for the marine variables, they're both here in this slide, and we also have them in the Orca help file. Okay, so in the Orca help file, there's a list of it's basically this list here of the marine, and anything that starts with the marine dot is considered to be part of the marine module. So these are all variables that are part of the marine module. However, there are many variables in here that are not part of the marine module, and the best way to find those variables is actually not in the Orca help file, but in the Cimerix help file. So I'm in Cimerix right now, and if I click help topics and bring that screen over here, one of the items in the contents is the expression editor here. So there's a whole discussion in the expression editor here, how you use it, what the syntax is, what functions. There's functions for doing operations like plus and minus and times and natural logarithm. So that's in here, but also in here are variables, and there's global variables like time. Here's the time variable that I just talked about. Pi is in there if you ever need to do a calculation with pi. If you just refer to something called X, Y, and Z, that is a position in the model somewhere at that given time. So these are globally available variables, but then each module has variables. So for example, the flow module has variables in it. So what you end up doing is if you wanted to see specific variables, you go to that module. So here's the flow module in the help file, and if I go to the description, here's an example of flow variables. So they start, unlike marine dot with the marine module, the flow modules, which are in here, you can see in my upper left-hand corners, I do have the flow module in the simulation, of course, because we're analyzing fluid flow. And these are available flow modules. So flow pressure, flow velocity, flow UVW, which are the components of velocity. So all these are in there in the help file. And so each module has its own variables available, and you can extract those here from the help file. So both a combination of the Orca help file for the marine specific variables and the Cimerix help file for all the other available variables would be your source for that information.